So, good morning to everyone. Uh, Today we discuss about the relation estimation theory. The syllabus is unbiased estimators, efficiency, consistency, and sufficiency, robustness, method of moments, method of maximum likelihood, the interval estimation of means, the difference between means variations, and a ratio of two variances. So first of all, we discuss about the unbiased estimators. So the introduction about the unbiased estimators. The problems of statistical inference are divided into problems of estimation and test of hypothesis. The main difference between these two types is that in the problems of estimation, we have to determine the value of a parameter or the several parameters from alternative, whereas in the test of hypothesis, we have to decide it whether to accept or reject a specific value or a set of specific values of a parameters. In an estimation problem, there is at least one parameter theta whose value is to be approximately on the basis of a sample. The approximation is performed by using an appropriate statistic. There are two types of estimation procedures. The first one is point estimation. The second one is interval estimation. So let's see what is a unbiased estimator, right? So, right, the first one is the point estimator, a statistic used to approximate or estimate a population parameter theta is called a point estimator for theta and is denoted by theta cap. So next one, point estimate. The numerical value assumed by the statistic when evaluated for a given sample is called a point estimate for theta. The next one, a definition of unbiased estimator. A statistic theta cap is said to be an unbiased estimator or its value an unbiased estimate if and only if the mean of the sampling distribution of the estimator equals theta. So whatever the value of theta, that is E of theta cap is equal to theta. It is the definition, right? Next one, the definition of biased estimator. So if the estimator is not unbiased, then E theta cap minus theta is called the biased estimator of the estimate theta. That means if the estimator is unbiased, then E theta cap minus theta is equal to 0. Right, next one. The more efficient unbiased estimator, a statistic theta cap is said to be a more efficient unbiased estimator of the parameter theta than the statistic theta 2 cap if the point 1 is theta 1 cap and theta 2 cap are both unbiased estimators of theta. The second point is the variance of the sampling distribution of the first estimator is no longer than that of the second and is smaller for at least one value of theta. So the next one, maximum error of estimate. Here Z alpha by 2 is the normal curve area to its right equals alpha by 2. It is noted that determinant x bar minus mu is the error in estimating mu by the unbiased estimator of the sample mean x bar. Let E denote the maximum value of determinant x bar minus mu. Then E is equal to z alpha by 2 into sigma divided by square root of n. So sigma is population mean. It's applicable for large samples, right? With the probability 1 minus alpha, that mean if we want to estimate mu with the mean of a large sample, n is greater than or equal to 30, it is a large sample. We can assert with probability 1 minus alpha that the error determinant x bar minus mu will be almost z alpha by 2 into sigma by square root of n. So let's see an example for the unbiased estimators. So problem 1. Suppose that we observe a random variable having the binomial distribution. Let x be the number of success in n trials. So this one is so that x by n is an unbiased estimate of the binomial parameter p. The second one is so that x plus 1 divided by n plus 2 is not an unbiased estimate of the binomial parameter p. So let's see the solution. The first one, we know that the probability mass function of the binomial distribution is p of x of x is equal to ncx into p power x into q power n minus x, where x is equal to 0, 1, 2, etc. Right? So the mean of the binomial distribution is e of x is equal to np, where n and p are parameters. Since e of x is equal to n theta, so e of x is equal to np, we know that. So here the p is replaced by theta, so we get e of x is equal to n theta. So we have to prove x by n, so that's why replace x by n. So e of x by n is equal to 1 by n into e of x. 1 by n is a constant, so is equal to 1 by n into e of x values n theta. So substitute the value of x value here n theta. So we get 1 by n into n theta. So we will get theta. Hence x by n is an unbiased estimate of theta. It's proved. Next, second one, b. We know that the mean of the binomial distribution is e of x is equal to so x bar is equal to np, right, where n and p are parameters. So e of x plus 1 equal to e of x plus e of 1 can be written as definition of the estimator. So which is implies e of x plus 1 equal to, so e of x value np, then e of 1 value 1. So e of x plus 1 is equal to np plus 1. It is equation number 1. So therefore e of x plus 1 by n plus 2 is equal to 1 by n plus 2 is a constant. Then e of x plus 1 is equal to 1 by n plus 2 into e of x. The e of x plus 1 can be written as e of x plus e of 1. So e of x value np, e of 1 value 1. So written as np plus 1 by equation number 1. So which is implies np plus 1 by n plus 2. So this is not equal to p. Hence x plus 1 by n plus 2 is not an unbiased estimate of p. So note that the common values for 1 minus alpha are 0.95, 5% level. That means 95% confidence level, 5% level of significance. So 5% level means level of significance 5%, it is a error. So and 0.99, that means 99% confidence level, 1% level of significance. So and the corresponding values of z alpha by 2 are z 0.025 is equal to 1.96 value, and z of 0.005 is equal to 2.575 respectively. Data. So it is value, is a table value. So next one. So the next is the second problem. In 6 determinations of the melting point of tin, a chemist obtained a mean of 232.26 degrees Celsius with a standard deviation of 0.14 degree. If he uses this mean of estimate the actual melting point of tin, what can the chemist assert with 95% confidence about the maximum error? We have to find the maximum error value. Solution. So substituting n equal to 6, the n equal to 6 value is given in the problem. So in 6 determination, that is the n value. Then a standard deviation denoted by S or sigma. So 0.14 and T 0.01 is equal to 365 for n minus 1 equal to 5 degrees of freedom's value into this formula for E. So we get E is equal to Z alpha by 2 into sigma by square root of n. It's a formula. So substitute the values Z alpha by 2. So sigma value 0.14 and n value root of 6 is equal to, so we get 0.19. Thus, the chemist can assert with 95% confidence that This figure for the melting point of tin is up by at most 0.19 degree. Right? So let's see another example. Example 3. Let x1, x2, x3 up to xn be a random sample from a normal population. So n of mu comma 1 show that t is equal to 1 by n, sum of I is equal to 1 to n x I square is an unbiased estimator of 1 plus mu square. Solution. It is given that n of mu comma 1, it is mu comma sigma. Right? So that means the mean is mu and variance. Sigma variance is 1 in the standard normal population. So which is implies E of x is equal to mu and the variance of xi is equal to 1. So we know that variance of xi is equal to the formula. So variance of xi is equal to E of xi square minus E of xi the whole square. So now we get E of xi square is equal to variance of xi plus E of xi the whole square. Right? So we will get so E of t is equal to E of 1 by n sum of I equal to 1 to n xi square. This is a given function, right? This is equal to 1 by n is a constant, so take it from the out of the function. So sum of I equal to 1 to n E of xi square. So E of t is equal to 1 by n into sum of I equal to 1 to n. So the E of xi square value is 1 plus mu square. So is equal to 1 by n into it is I equal to 1 to n, so that's why n into 1 plus mu square. So n and numerator n and denominator n will be cancelled. So we will get E of t is equal to 1 plus mu square. Hence t is an unbiased estimator of 1 plus mu square. So thank you to everyone.